Moving on to immunofluorescence is another type of diagnostic test. Immunofluorescence is a light microscopy-based technique mainly used on body tissues and cells. It detects antigens bound to antibodies that have been tagged with fluorescent dyes. So it's pretty simple. You can see it on the image at the bottom here. So you're just getting an antigen-antibody complex, and the antibody has been tagged with a fluorescent dye that we can measure through light microscopy to determine whether the antigen is in the solution. Moving on to another type of diagnostic test, radioimmunoassays, RIAs. These use the same kind of principle as ELISA tests, in the sense that there is a direct binding between the assayed antigen and antibodies. These are typically used for measuring hormone levels, and a brief explanation is that radioactively labeled antigens are added to the section with complementary antibodies. So shown on the image here, these little blue antibodies bound to the bottom of the well would be these complementary antibodies, and these little red circles are the radioactively labeled antigens at the image on the top right here. These antigens that are radioactively labeled bind to the antibodies. Then the patient's blood containing non-reactive versions of these antigens are added to the solution, shown by these little kind of white antigens shown on the left here as the unlabeled antigen. Some of these unlabeled antigens are going to displace some of the radioactively labeled antigens bound to the antibodies. They're both complementary. And then we basically just measure the unbound antigens. So unbound antigens would be separated, and the number of radioactive antigens still bound to the antibodies are measured. So less radioactive means that there's more antigens in the blood, because more of these radioactive antigens have been displaced. So all that's happening when we're measuring it, we're taking out all the free-floating antigens, be they unlabeled or labeled, and then we're going to measure the radioactivity of these antigen-antibody complexes. If they are less radioactive, then that means that more of the radioactive red antigens have been displaced by the non-radioactive white antigens, meaning that there are more antigens in the patient's blood. Now moving on to a Coombs test, which looks at a process called hemagglutination. A Coombs test is used for blood typing and for identifying viral infections. Glycoproteins on viral surface proteins interact with the red blood cells, causing them to clump together. With regards to blood typing, antibodies specific to erythrocyte surface antigens are used. There are two different types of erythrocyte surface antigen. You either have type A or type B, and then some people can either have neither of these surface antigen, which would be type O, or they can have both of this type of antigen, shown as type AB in the bottom right there. If the antibody is added that targets the A antigen, so we add an antibody that recognizes the A antigen, and hemagglutination occurs, then we know that the blood type is going to either be type A or type AB, because the antibody has recognized that there are A antigens on the erythrocytes because they've clumped together because the antibodies have bound to them. We can differentiate AB antigen-specific antibodies between A or B through the use of a B antibody. If we add the B antibody and no hemagglutination occurs to these already, so we already know that it's either type A or type B because we've added the antibody that recognizes the type A antigen and hemagglutination has occurred, so it's either type A or type AB. We would then add a antigen that targets the B. We would then add an antibody that targets the B antigen. And if hemagglutination does occur with this B antibody, then we know that the blood type is AB. If hemagglutination doesn't occur when we add this B antibody, then we know the type is just type A. If hemagglutination doesn't occur with an A antigen-specific antibody or a B-specific antibody, then the blood type is going to be type 0, type O. Hopefully that kind of made sense. It's a bit of a mouthful when you're kind of trying to explain this within a certain time frame. The general idea is that we're just using an antibody that targets either the type A or the type B antigens shown on these red blood cells at the bottom here. So you can imagine we would use an antibody that would target the purple type A antigen. If the antibody binds, then we get hemagglutination and these blood cells clump together. If they clump together when we add the type A antibody, then we know that it definitely has this purple antigen, so it'll either be type A or type AB. We then differentiate whether it's type A or type AB by adding the B antibody that recognizes the green antigen, and if it doesn't clump together after that, if no hemagglutination occurs, then we would know that it's the type A because only the type A antibody has caused hemagglutination. But if the type A and the type B antibody both cause hemagglutination, then we know it's type AB. And if neither of these cause hemagglutination, then we know it's type O. So hopefully that kind of summarized a bit for you. Like I usually say, it's better to kind of read the slides. I've made these slides so that you can just read them and you have like a full understanding of the topics, even if my explanations aren't great. So moving on to disease diagnosis, as a quick kind of end to these couple of videos on immunodiagnostic techniques, we need to look at the sensitivity and specificity of a test to statistically determine how useful it is. And sensitivity and specificity are inversely related. A positive predictive value is the ratio of patients truly diagnosed positive to all those with a positive test, so all the positives and the false positives for the positive predictive value. And a negative predictive value is the ratio of patients truly diagnosed negative to all those with negative test results. So all negatives and all false negatives. I've put a couple of calculations at the bottom here. We calculate sensitivity as the proportion of true positive tests, so true positives over true positives plus false negatives. And we calculate specificity as the percentage of true negatives out of all individuals who don't have the disease. So we just do true negatives over true negatives plus false positives. Just have a quick read and have a think about why that actually is. It's basically just a couple of calculations that allow us to know how useful these tests actually are.